Hi class, welcome to lesson 36, the last and final lesson in unit number 5, bonding and intermolecular forces. By the end of this video, you should be able to determine the type of intermolecular force that exists between covalent compounds and determine the effect of intermolecular forces on melting point and boiling point. In today's lesson, we are going to look at intermolecular forces. These forces are different than the bond force we've been looking at previously. Recall that ionic bonds, covalent bonds, and metallic bonds are what hold two different elements together to create a compound. These bonds create different chemical properties for a substance. It is known that ionic compounds have faster chemical reactions than covalent chemical compounds. But today we are going to look at intermolecular forces. These are forces that are between molecules. They are what determine the physical state of matter, like whether or not a substance is a solid with strong intermolecular forces, a liquid with intermediate intermolecular forces, or a gas with basically no intermolecular forces at all. You can see here that the intermolecular force is drawn with a dashed line. It is a force between two molecules. It is much weaker than a bond, and it is not as permanent as a bond. Liquids, on the other hand, have a moderate intermolecular force, creating a definite volume but an indefinite shape. And solids have a very strong intermolecular force, causing the particles to vibrate in a fixed position, giving a definite shape and a definite volume. Recall that we learned about intermolecular forces in Unit 1. Intermolecular forces describe why some substances are solid, liquid, or gas at STP. Oxygen is said to be a gas at STP because it has very weak intermolecular forces. These weak intermolecular forces give oxygen and other gases indefinite shape and indefinite volume. That's why gases always completely fill their closed containers. We are going to learn about 4 major types of intermolecular forces. Take a minute to pause the video and copy down this chart so that you can take notes on the molecule-ion force, the dipole-dipole force, the hydrogen bonding, and the van der Waals dispersion forces. You must be familiar with all types of intermolecular forces by the end of this video. The molecule-ion force is a force between a polar molecule and an ionic substance. A molecule-ion force results when the positive end of a polar molecule attracts a negative ion and vice versa. Notice how the water molecules change their orientation so the more positive hydrogen atoms are closer to the negative ion. Here is another simplified picture of a molecule-ion attraction. The green oblong shapes are polar molecules, and you can see the individual ions from the ionic compound sodium iodide. Notice how the positive ion is attracted to the negative end of the polar molecule, and the negative ion is attracted to the positive end of the polar molecule. This explains why most ionic substances dissolve in polar water. Here is another example showing how sodium chloride dissolves in water. Take a minute to pause the video as this will be an open-ended question on an upcoming assessment. Notice how water changes its orientation relative to the ion that it surrounds. So when water surrounds chlorine, the more positive hydrogen ions are in, while when water surrounds sodium, the more positive hydrogen ions face out. The next type of intermolecular force is called a dipole-dipole force. A dipole-dipole force exists between two polar molecules. Recall that molecules are polar when they're asymmetric. We can use the shortcut and look for an odd subscript. So in dihydrogen monosulfide, the subscript is 1, or phosphorus trihydride, the subscript is 3. These polar molecules will have a dipole-dipole force of attraction. In the dipole-dipole force, the more electronegative atom will be attracted to the more electropositive atom of a different molecule. Again, this is not a bond, but it's a force that holds molecules together and allows them to be liquids and solids. In this simple diagram of a solid dipole-dipole force, you can see how negative charges align with positive charges of other molecules. Here, opposites attract. Now, when in the liquid state, the dipole-dipole force is a little bit more messy to illustrate, but the same thing happens. Opposite charges of different molecules attract one another. And of course, like charges repel. You can see the attraction with the red dashed line. So we use the intermolecular forces to determine which compound will have a higher boiling point. It is always true that polar compounds have higher boiling point than nonpolar compounds. So between HCl and fluorine, we know that HCl, which is polar because its last subscript is 1, will have a higher boiling point. And between silicon tetrahydride and phosphorus trihydride, the phosphorus trihydride, which has an odd subscript of 3, will be polar. It'll be asymmetric and polar and have a higher boiling point. The next type of intermolecular force is called hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole force. Hydrogen bonding is approximately 5 times stronger than a dipole-dipole force. It occurs when hydrogen of one molecule is attracted to fluorine, oxygen, or nitrogen of another. So remember, hydrogen bonding involves fluorine, oxygen, and nitrogen. Water molecules have hydrogen bonding. Hydrogen bonding accounts for water's very high boiling point, which gives it unique properties, allowing it to create our blue planet that sustains life here on Earth. You can remember hydrogen bonding is FON because hydrogen must bond with fluorine, oxygen, or nitrogen. Hydrogen bonding is not a bond, it's actually an intermolecular force. This graph shows us the impact of hydrogen bonding on boiling points. So notice that as we go down the group and we increase the size of the atoms bonded, we increase the boiling point. But when we look at substances that have hydrogen bonding, their boiling points are extremely high. That's because the strong intermolecular force found in water, hydrogen fluoride, and ammonia create higher boiling points. Notice that all of the molecules contain hydrogen, but only the molecules that contain fluorine, oxygen, and nitrogen contain hydrogen bonding. When we look down group number 14, you can see that all of these molecules are bonded with hydrogen. But none of them have fluorine, oxygen, or nitrogen. So here we see the expected trend that as we increase the size of the atom bonded, we increase the boiling point. This is a nice and steady curve. Again, the presence of hydrogen bonding is what explains the uncharacteristically high boiling points of the water, hydrogen fluoride, and ammonia. The final type of intermolecular force we will discuss are called van der Waals dispersion forces. The van der Waals force exists between all substances. It is a force that exists between atoms, which are inherently nonpolar because they have a positive nuclear center and negative electron cloud surrounding. They are also the only type of intermolecular force found in nonpolar molecules. Nonpolar molecules are expected to have very low melting points and boiling points. But dispersion forces explain why as we go down group number 17, we begin with fluorine, a gas, and chlorine, a gas. But then we have bromine, a liquid with an intermediate intermolecular force, and iodine, a solid. Dispersion forces are the result of moving electrons. All substances, including atoms, have electrons, and since they're in constant motion, there can be a time where the electrons happen to all be on one side, creating a temporary dipole. The more protons and electrons an atom has, the stronger the temporary dipole they can have. That's why, as we increase the mass of a molecule, we know we are increasing the number of protons and the number of electrons, and we are increasing the dispersion force. Increasing the mass will always result in an increased melting point and boiling point. So when we look here at these 4 organic nonpolar compounds, we can see as we increase the number of atoms in the bond, thus increasing the mass, we are increasing the boiling point. We know that each of these molecules must be nonpolar because their last subscript is even. Their last subscript is even, allowing them to create a symmetric shape and be nonpolar. So by now you should be able to determine the intermolecular forces that exist between covalent compounds. Again, make sure that you are able to correctly orientate water relative to ions in a dissolved ionic compound in an aqueous solution. Intermolecular forces are important because the more intermolecular forces present, the higher the melting point and boiling point of a substance. So when we compare hydrogen to water, which have very similar properties, we need to explain why water is a liquid and hydrogen is a gas. Water is a liquid because it has much greater intermolecular forces than hydrogen gas. Recall that gases have no intermolecular forces. Why does hydrogen not have any intermolecular forces? Well, hydrogen is a nonpolar molecule, so the only intermolecular force present could be a van der Waals dispersion force, the weakest intermolecular force of all. Water, on the other hand, is a polar molecule. Its last subscript is odd, so it has a dipole-dipole force. Water also has a very strong hydrogen bond because it contains hydrogen and oxygen. So by now, you should be able to determine the effect of intermolecular forces on melting point and boiling point. More forces, the greater the melting point and boiling point are. Here is a nice chart that you can copy in your notes that summarizes the different types of intermolecular forces and compares the strength of each force. This concludes lesson number 36. You should be able to determine the type of intermolecular force that exists between covalent compounds and determine the effect of intermolecular forces on melting point and boiling point. Make sure that you've taken good notes and bring those notes to class so that you can revise and add to them. Write down any questions you have and ask them. We are here to help you better understand. Complete your homework on Google Classroom and don't forget to put your Regents Chemistry reference table and calculator back in your backpack so you are prepared for class. I'll see you soon.